Well, hello everybody. Thank you for joining me today. So, as I said in the chat, today what we're going to be working on is just going over the homework examples from chapter 15 and 16. So if you guys have any problems in particular you want to do, please let me know which ones. Write it in the chat so I can get to them as I do them, or shout it out at me. Otherwise, I'm just going to start talking about stuff. Alright, so the first one I see is chapter 15, number 14, so I'll go ahead to there. So what we're posed with doing here is we're trying to find the group generated by 1, 4, 3, 2, and 2, 4, so the permutations in S4. So what we want to do is figure out, okay, we need to close this set under products and figure out what and identities and inverses and figure out all of the permutations thereof. So let's go ahead and start working through that. The first thing I'm going to start with is actually the smaller one because it'll be a little bit easier. We have 2, 4. So we know that if we have to close this under identities and inverses, well, we're going to have to add in the identity permutation, which just sends everything to itself, which we've been denoting by 1. I also have to add in 2, 4 because it's in there. So I'd have to compose 2, 4 with 2, 4. But if I compose 2, 4 with 2, 4, you'll notice that this is, well, 1 goes to 1. 2 goes to 4, goes to 2, so 2 goes to 2. 3 goes to 3. 4 goes to 2. 2 goes to 4, so 4 ends up at 4. So this is just the identity, which we already had in there. And actually, you'll notice then that 2, 4 is its own inverse. Therefore, right now, we have that, we could say the group generated by 2, 4 is just the set consisting of 2, 4 and the identity. And so we have it closed right now. But we also have to add in the other element, 1, 4, 3, 2, that was included in my generating set. So now I have to close this again under compositions, inverses, and identities. So I'm just going to look at, okay, I have this in there. So what is 1, 4, 3, 2 composed with itself, let's say. So let's actually go through. If I watch, I'm going to start at 1. 1 goes to 4. 4 goes to 3. So I get 1, 3. Now if I move on to 3, 3 goes to 2. 2 goes to 1. So 1 goes to 3. So I closed off that cycle. So then I'm going to start over with 2 because it's the next smallest. So here I get 2 goes to 1. 1 goes to 4. So 2 is going to go to 4. And then I get 4 goes to 3. And 3 goes to 2. So 4 ends up at 2. So we close off that cycle. So what that means is that we also have 1, 3, 2, 4 in the group generated by 2, 4 and 1, 4, 3, 2. All right. Now we're going to have to do that again. So what happens if I take this cubed? So here is one element. I'll write it up here. So now I'm going to compose this with 1, 4, 3, 2. And so I start over and I say 1 goes to 4. Then 4 goes to 2. So 1 ends up at 2. Then we'll start at 2, and 2 goes to 1. 1 goes nowhere. 1 goes to 3, so 2 goes to 3. Sorry, I'm not supposed to close that off yet. I move on to 3, so 3 goes to 2. 2 goes to 4. 4 stays where it's at, so I get 1, 2, 3, 4. And so what I'm left with is I still have to check 4 goes to 3, 3 goes to 1, so 4 goes to 1, so I get the permutation 1, 2, 3, 4, so I can add another one in here. Alright, so maybe you guys can help me out. What should I do next? Oh, James, we are doing chapter 15, number 14. Sorry, T, how about what? So we can compose 2, 4 and 1, 3, 2, 4. So if we do that in either direction, I think we're going to get the same thing. We get 2 goes to 4, 4 goes to 2. These just end up canceling out, right? And so we're just left with 1, 3. So we will indeed get 1, 3. Um, that's great. Now really we just have to kind of keep doing this. So I've done 1, 4, 3, 2 with itself. So squared I get this. Cubed I get this. I should do it again. So what is 1, 2, 3, 4 composed with 1, 4, 3, 2? Well, I would get 1 goes to 4 goes to 1. So that's just 1. 4 goes to 3 goes to 4. So 4 goes to 4. 2 goes to 1 goes to 2. And so if I compose these two, or if I put this to the fourth power, I'm going to end up with the identity again. So that was nice to check that, okay, I got to the fourth power, I end up at the identity. So I have this one, this one, this one, and this one is the group generated by 1, 4, 3, 2. And so now I have to compose 2, 4 with each of these. So I composed to here, I got 1, 3. If I take 1, 4, 3, 2 composed with 2, 4, I'm going to get 2 goes to 4, 4 goes to 3. I should say, I'm going to start off with 1. 1 is going to go to 4. 4 is going to go to 2, it goes to 1. Then 2 goes to 4, goes to 3. And 3 goes to 2. So we get 1, 4, 3, 2. And then let's see, so we did 2, 4 composed with this one, this one. Let's do 2, 4 composed with this one. We're going to get 1 goes to 2. 2 goes to 4 goes to 1. 3 goes to 4. 4 goes to 2 goes to 3. So we get 1, 2, 3, 4. And so we keep adding in more and more. And no, actually, I'm not even going to finish this, but somehow you just have to make sure that you check every single pair. And so I'd have to say, okay, I did these two. I did this with itself twice, this with itself twice, this with this. I did this with this. And I just keep going through until I get new ones and new ones, until finally I realize that I've gotten everything that I can get. So really, to find the group generated by these, I'm going to keep finding the compositions of these over and over again. Now, this problem is a bit of busy work because the reason why I gave it to you is so that you get more work with permutations, making sure what does it look like when I compose these permutations. And notice again, we also do have to compose in both directions. That is, this on the right and this on the left, and this on the left, this on the right. So you have to just keep going through until you finally get that you have a closed set under compositions. It's not a trivial thing to do. It takes some time. But that was the point of the homework, is to get you used to working with these and finding these compositions. Does that make sense to everybody? So I have the wrong question. That's the problem. Let me pull up the thing real quick. I had copied these off in the book. I thought I'd copied them correctly. But 15, okay, I see. I did 15.13 instead of 15 point. I'll pull this up. I had done 15.13 instead of 15.14. So if the empty set denotes the empty set, what is the group generated by the empty set in any group? All right, that's a great question. So, well, actually, I'm just going to leave that one up. We can just talk about that. So, what is the group generated by the empty set? You guys help me out. What is this? That means that it's the smallest group containing the empty set, which means it's the smallest group containing anything, which means it's just the smallest possible group. What has to be in a group? That is correct. There has to be an identity element in a group. And then if I have an identity, I also have to be closed under products and inverses. But the identity product itself is just the identity, right? And the inverse of the identity is the identity. So if I have this set consisting only of the identity element, it is a group. Therefore, the smallest group containing the empty set is just going to be the set consisting of the identity of the group. So for any group, the group generated by the empty set is just going to be the trivial group, or that is the group consisting of the identity element. Does that make sense? Okay. So if we look back at this one, notice what I did is I started with these elements, and I said, okay, it has to be closed under these properties. So what I'm going to start with is nothing, because that's the empty set. And I'm going to say, okay, if I want to find the group generated by nothing, I have to close it under compositions, and I have to close it under inverses, and I have to close it under identities. And so what I said here was I started off with the set, and I said, okay, we have to close it under identities, so the identity is going to be in my group generated by that. It doesn't matter what my generators are, or if it's even nothing, I still have to have the identity element in there. So I could say the identity on G has to be in the group generated by the empty set. Does that make sense so far? Okay. Then what I'm going to do is I'm going to continue to close this. Sorry, go ahead, James. So I'm generating from the empty set. So I start with nothing. And so to get the group generated by any set, I'm going to close it under the product, an identity, and inverses, because those are the properties of a group. Now, I should say that we also have associativity, but because I'm going to generate it as a subset of a group, I'm going to have associativity. So I have to close it under products, identities, and inverses. So because I have to close it under identities, notice, actually, I started with products. And I said products, if I close the empty set under products, I get the empty set and nothing new comes out. Because there's nothing to multiply, right? So I don't get anything new out by products. So I'll move on to identities. Let's put the identity in there. All right. Now that I put the identity in there, I'm going to go back to products. So each step of the way, if I add something, I go back to products and close it under products. Now, what is the identity times the identity? Well, that's just going to be the identity, so we don't get a new element. So I'm going to say this set is now closed under products. So I'm going to go through my list. Closed under products. Is it closed under identity? Yes. And now I'm going to go to inverses. So I'm going to have to add in any inverses I might need. So what is the inverse of the identity element? So 1 over the identity would just actually be, well, if we think about it with respect to real numbers, 1 over 1 is just 1, right? So in general, what we would get is the identity times the identity is the identity. So the inverse of the identity is just the identity. So because the inverse of the identity is the identity, we have that this is indeed closed for inverses. Now, if we had a different element, like another inverse, I'd have to go back and make sure it's then closed under products, and then closed under identities, and closed under inverses again. So I just keep going through, starting over each time I add a new element, until I'm closed for these 3 things. Now I've done that starting with nothing. I've gone through and done that, and what I've ended up with is just 1 element. What that means is the group generated by the empty set is just the set consisting of the identity element. It is a group, and it does contain the empty set, and it is the smallest group which would contain the empty set, because starting with the empty set, I had to get that element in there. I'm sorry, what was that? So if you didn't have this property, you didn't have to have an identity. You could say the thing generated by the empty set closed under products, for example, would just be the empty set. That is correct. But because we have to have an identity, we have to have something in there. So we have to have an identity element. So we have to put that in. So therefore, if it's the thing generated by the empty set, because I have to close under here, becomes the group consisting of just the identity element. Does that make sense? All right, very good. All right, so next you had 27. So if I look at 27, I'm just going to ask you before I start proving this, is that the correct question? All right. Well, I didn't get an answer there, so 15.27. Prove. Oh, I was asking you guys, but that's okay. Prove that if the group generated by A is equal to the group generated by B, or that prove that that's true in Z sub n, if and only if. And they're using a different notation here than I am, but they're saying the greatest common divisor of A and N is the same as B and N. I know that's probably small on your screen when you're looking at this, which is why I typed them up so that we could see them better. So we'll go back to that. So what I have is, so the group generated by A is equal to the group generated by B and Z sub n if and only if the greatest common divisor of A and n is the greatest common divisor of B and n. All right. So how would we do that? So I'd have to show that this is a subset of this. And then I'd have to do the reverse to show they're equal. And so I'm going to have to do that. But remember that when we're showing groups generated by elements, if I want to show that this is a subset of this, I really just have to show that A is an element of B. So now we did this in class, and we proved the theorem that when we're working with groups generated by sets, if we can show that the generators are in the set, that's enough to show that this group is a subset of this group. So we don't have to show every element, we just have to work with the generators. Do you guys remember that? All right, good. So I have to show that A is in here. Now notice when I do the other direction, the proof's actually going to be exactly the same, except you're going to replace A and B. So really, if we can just get this much, we'll be fine. Because everything else will follow by a similar proof replacing A and B. So I have to show, so I'm going to write it down here, show A is in the group generated by B. Then, or I should say to start, what I want to know is what does the group generated by B look like? Actually, I guess working backwards here, if I want to show A is an element of the group generated by B, I have to show that A satisfies the properties that it's in the group generated by B. So the group generated by B is going to be what? We actually went through and we said the group generated by any element is the set. In general, it'd be something like B to the n such that n is in Z, right? But because we're using addition here, because we're in Z sub n, what we're going to end up doing is just using addition writing to say that this is going to be the set of all B times n, such that n is in Z. Because B plus B is 2B, plus B is 3B, 4B, 5B. We get 0B is the identity, negative B is the inverse. And so just B times n such that n is in Z would be the set here. And so I have to show that A is an element of that. So now, if we were using product notation, that would just mean that. So that would mean that we'd have to be working with a group with multiplication. So something like show that the positive rationals under multiplication, then I want to show the group generated by A is equal to the group generated by B if and only if something. Then we'd have to show that A looks like B to the, let's say, M for some M in Z. That's how, if we had a product here, that's how we're going to use it. Now we could still use this notation. We could still say B to the M, and I'm going to change it up to M instead of N, because N is already in the problem, so I don't want to mix those two up. I had forgotten about that, but I do want to use a different integer here. But I'm using additive notation just because we're using addition on the integers. That way I don't have to kind of go back and forth in my mind between what I'm talking about and what I'm writing. So what this means is if I want to show A is in this set, I really have to show that A is equal to B times M for some M in Z. Now, I should be careful here because remember that this is B times M is taking place in Z sub n. So what I really want is A is equal to B sub B times M in Z sub n. So what I really have to show is A is congruent to B times N mod N. So this product isn't just B times N as in the normal integers, but rather it's occurring within the integers mod N. So when I'm saying A is equal to B times M, what I really mean is A is congruent to B times M mod N. Is that okay with everybody so far? So what I have to do is I have to show there exists an M such that A is congruent to B times M mod N using, and now what I get to assume is that the greatest common divisor of A and N is equal to the greatest common divisor of B and N. All right. How are we going to do this? Any ideas how to get from here to here? Oh. So we can use equivalence classes here, and we can say, okay, what is the equivalence of class of B? What is the equivalence class of A? And I can actually find, if I wanted to, I can actually find what the group generated by A looks like in mod sub n. I'm going to just say here that since this is all I really need to prove, I'm going to stick with that. But what I do need to do is I need to use this fact and recall that there was this nice thing about greatest common divisors. And if you guys didn't see this, that makes sense. But if you go back over what we did in class and what's in the book, what we have is that there exists integers. Let's see, what integers have I used so far? Okay, I can use a k1 times a plus L1 times n is equal to the greatest common divisor of a and n. And there exists a k2 times b plus L2 times n, which is equal to the greatest common divisor of a and n. So now we went through and we proved this, and that actually was an involved proof. That was the whole, we had to use the division algorithm over and over and over again, and then we get to the bottom, and the final remainder has to divide the previous ones. And so then when we were all together, we said, oh, if we rearrange it, we get something that looks like this. And so this is a really nice theorem that we end up using quite a bit in abstract algebra. And so if I have the greatest common divisor of two numbers, I can always write an integer times a plus an integer times n is equal to the greatest common divisor of a and n. An integer times b plus the integer times n is equal to the greatest common divisor of a and n. Following me so far? All right. Now, I know this is a little counterintuitive, but now I'm going to use Killer's remark that I want to use equivalence classes, because instead of trying to show directly that this is B, I'm actually going to take a step back and I'm going to show that. So I'm going to need to do the same process, but I'm going to show that the group generated by A is actually the group generated by the greatest common divisor of A and N. Now, why this is going to work is if I can show this, that would mean that the group generated by B is the group generated by the greatest common divisor of B and N. But since we assume these two things were equal, these two groups have to be equal, therefore A has to be equal to B transitively if I work my way around. And the reason why I'm going to do this is because it's a little easier to go from here to here than it is to go 2 steps at once. Again, that's not an obvious thing to do. It's something that you kind of do because you get used to practicing and seeing things. So if I go back over the things at the bottom, what this was saying is that I have to show that A is equal to some integer, let's say m, times the greatest common divisor of A and N. Now, to show that this is a subset of this, I have to show this. Is this going to be true? What do we know about the greatest common divisor of A and N? It is a common divisor of A and N. Therefore, does this divide A? Yes, it does. It does divide A. Therefore, there has to be some integer such that the integer times this is equal to A. Therefore, A is definitely a subset, or the group generated by A is definitely a subset of the group generated by the greatest common divisor of A and N. So what I really have to do is I have to show the other direction. So I have to show that the greatest common divisor of A and N is congruent to, or is equal to, A times M for some integer M in Z sub N, which means that I have to show that these are congruent mod N. So now I'm kind of doing the same argument I had before, as if I want to show that the group generated by this is a subset of the group generated by A. I have to show that this is in the group generated by A. Therefore, I have to show that this is a multiple of A. But I have to show that within Z sub N. So I have to show this is a multiple of A mod N. Now we're almost ready. Well, if I use this, I get that the greatest common divisor of A and N is equal to K1A plus L1N for some integers K1 and L1. The only thing left to do is notice, what is this congruent to mod N? Well, mod N, this is congruent to K1A plus L1. What is N congruent to mod N? It's just 0, isn't it? So mod N, I know that from our theorem, the greatest common divisor is K1A plus L1N, but this is just congruent to 0 mod N. So this is just congruent to K1A mod N. And lo and behold, what have I just proven is that the greatest common divisor of A and N is a multiple of A in Z sub N. Therefore, it is in the group generated by A. Therefore, the group generated by A is the same as the group generated by the greatest common divisor of A and N, which is equal to the greatest common divisor of B and N, which is equal to the group generated by B. Hence, the group generated by A is the group generated by B. There was a lot going on there, wasn't there? That was a really fun proof. I like that. That's why I put it in there. It's supposed to hurt a little bit. Your head's supposed to hurt a little bit the first time through. And a lot of these that I put on here, not all of them are supposed to be easy. A lot of them are. I want you to get it wrong a couple of times. And that's why we're going over and reviewing these together so that I can show you how to do this. This definitely isn't something I would ask you to do on a test. but it is something I'd ask you to do on the homework, to spend some time with and get as far as you can. And when you're writing up the homework, if you don't get the whole thing, that's fine. You just do as much as you can to try to explore some wonderful stuff about algebra. However, now that we've done it together, what I would say is good practice for you is just rewriting that as a formal proof. There's a lot of I went sideways and back and forth and jumped over because I tried to follow an intuitive line of this is what I want to try, this is what I want to try, so I'm going to try this. But if you try to write it up linearly in a formal proof, that'll help you kind of collect your thoughts so that you can really see what happens. And since you have this on video here, I'll let you guys, I would highly suggest you do that for tonight's homework, is go back and try to write this as a formal proof from the work that we did together. Does that make sense? You are correct. It is extremely difficult to get on your own, just intuitively guessing and trying to figure out what you're coming up with. But that's why I'm giving you these, is because once you get through and you see me do it now, you start to see little things and connections that I make. So as someone who's done this a while and has practice, you make connections between different ideas. And those connections are what I hope that you guys can start to make. You don't have to make all of them, but if you make one or two, I'm really happy for you. That is what I'm trying to get you to do. So if you start seeing things like, oh, well, I have to remember this thing about this formula that we used, which is, and that formula is called or related to the Chinese remainder theorem, if you need a name for it. But we use that a lot, and so I'm going to use that, and so I'm going to use this and that, and I'm going to try to put these things together so I get out this nice result. And so this is actually a really nice result to know, is that if I'm finding the group generated by any element in Z sub n, I can instead look for the greatest common divisor of A and N. Any more questions on that one? All right. So what I want to prove here, so 15.29 was the next question. I want to show that every subgroup of Z under addition is cyclic. All right. Now, in the book, they outline how to do this one, but I'm actually going to do it a different way. So that's what the proof will follow the outline. In the book, they actually try to walk you through it step by step, and you're welcome to do that. But just to kind of reinforce what we just did, I'm going to use a proof very similar to what we just did. And so if I want to show every subgroup of Z is cyclic, I'm going to do this inductively. So, if I'm going to do this inductively, what does that mean? Is that if I find the group generated by A, it is cyclic by definition, right? So I'm going to do it inductively on the number of elements in the generating set. So let's suppose that there are, let's just do two elements at a time. So let's suppose that I have A and B. So the group generated by A and B in Z. If I want to prove that this is cyclic, I have to show that I can write this as the group generated by one element. Does that make sense? So not has only one element, but is generated by one element. That is, all the things in here can be found using one generator. We will have more than one element, so if this is like 2 and 3, 2 will be in there, 4, 8, all the multiples of 2, but 3 will be in there, all the multiples of 3, and so on and so forth. And we're going to have lots and lots of elements in here, but what I want to show is that this can be also be found just using one generator. And the way I'm going to do that is intuitively guess, what do you think that generator would be? This is why the book doesn't do it this way, is because this intuitive guess, what is the generator? So now the identity might be right, but it's not always going to be right. What did we say it was equal to last time? Is the greatest common divisor. So now if we want all of z, that's going to be true. But what I'm going to claim is the group generated by AB is going to be equal to the group generated by the greatest common divisor of A and B. Notice that's kind of what happened last time, is we had a group generated by A, and Z sub n was the greatest common divisor of A and N. And so I'm kind of trying to find similarities here, and I'm just making this as an arbitrary guess, and I'm going to claim that these two things are equal. So that's my claim. And if that's true, that means that the group generated by AB is going to be cyclic, because it is then generated by one element. Makes sense so far? Now, when you guys were saying 1 or negative 1, if these are co-prime or the greatest common divisor is 1, then the group generated by AB is going to be the group generated by 1. But that's not going to be the case if these have a common divisor. So in general, we're going to have to work with the greatest common divisor. Now, just to recall, what we get is that A times K1, that this is equal to, the group generated by A times B, is any multiple of A plus any multiple of B. And this is equal to any multiple of the greatest common divisor of A and B. So what do I need here? Let's say H1. So now I'm going back to that and saying we actually found that if we want to find the group generated by elements using additive notation, we would take all multiples of A and all multiples of B, and since we have to close under addition, we would add those things together. If we have just one element, it's just going to be all multiples of that, which we did talk about in the last problem. Does that make sense so far? All right. Now remember, I want to show these are the same, so I want to show each one's a subset. So I'm going to start with show that AB is a subset of the group generated by the greatest common divisor of A and B. What I have to do is I have to show that A is in this and B is in this. So I just have to show the generating elements are in this group. But remember, the things in this group are multiples of this. So is A a multiple of the greatest common divisor of A and B? Help me out here, guys. Why? Well, because the greatest common divisor, it is a divisor of A. Since this is a divisor of A, that means A is a multiple of this. Hence, A has to be in here. And by the same reasoning, B has to be in here. So that direction is actually pretty easy. To show the other direction, what I have to show is that the greatest common divisor of A and B is going to be in the group generated by A and B. But what does that mean is I have to show the greatest common divisor of A and B can be written as a linear combination of A and B. So that is, it's equal to AK plus BL for some integers K and L. So this is what I have to show. Alright, hopefully you guys are seeing why I'm doing it this way. Is that true? It is a long process. But notice that we know this is true because we just used that in that last one, and this was the Chinese remainder theorem, right? So I gave it a name 10 minutes ago, or 2 minutes ago. But we know this is true because we proved it in class. So the greatest common divisor is a linear combination of A and B. Therefore, the greatest common divisor is in this group. So this group is a subgroup of this group. So these two groups are indeed equal. Make sense? What happens if I had 3 elements in here? Well, if I had 3 generators, then these two could be condensed down to the greatest common divisor. And then I could then find, those are now just 2, so I could condense it down to 1. So if I have 2 elements, I can make that 1. And then 3 elements then becomes 2, which then becomes 1. So this is then also going to be a cyclic group, which is going to be the greatest common divisor of A, B, and C. And then if I have 4, I'm going to again be able to condense it down to 1. And in general, what I get, and that's exactly what I'm saying, is that if I have a set T, then the group generated by that set T within the integers is just the group generated by the greatest common divisor of T within the set of integers. So even if this is, so for any finite group, we get that inductively this is going to be true. Now if we work with infinite subsets, that's one of the reasons why they work through a different way, is that then you'd have to define the greatest common divisor of an infinite set. But if you do that properly, you can also get that, yes, even for an infinite set, we're going to get, if I can find the greatest common divisor of that set, that is going to be the generator of this group. Therefore, every subgroup of Z, even when I have infinite subsets of Z, I can always condense it down to the greatest common divisor of that set is going to generate that set. So therefore, every subgroup of Z is indeed a cyclic subgroup. Now, the way that they walk through it is actually very similar. So they just said, suppose I have a set, then what I can do is find the smallest element of that set, smallest non-negative, or sorry, smallest positive element of that set, because every set of integers, every positive set of integers has to have a least element. So therefore, if this has a least element, the least element is going to be the generator. But the least element will also be the greatest common divisor. So therefore, you're going to get a very similar proof both ways. And so I'll kind of let you look at that however you want it. The reason why I chose to go this route was just to reinforce the ideas that we had just talked about in the previous proof. Does that make sense? Now, and you'll see quite frequently that there's multiple ways to give different proofs, and there's nothing wrong with that. You just want to find a way that works for you. Like I said, the benefit of theirs is that it's a little bit easier to transition into an infinite set than when we're working with the technique that I used. So since we want this to be true for all sets, we also need infinite sets. So if we work through their proof, it's going to work all the time, whereas mine will work for any finite set. To make the jump to infinite, we have to start redefining greatest common divisor and things. But I thought it was worth going to try to reinforce that idea with you to help you out on that. Alright, so I'll leave that one for you guys to look at some more if you desire. Otherwise, I am going to move on to our next question, which is Chapter 16, number 5. Alright, So we want to determine the right cosets of 1, 2, 3 in S3. So what ends up happening is this ends up following very similar to what we talked about earlier, or the one I was doing that didn't necessarily need me to do, that I'm just writing things over and over again, and you have to do a lot of work here. So what we end up with is I'm actually going to end up making just the Cayley table, which we've done before, to make this work a little bit easier. Sorry, I'm just trying to change it to the chalkboard. So what I would say is this is going to be just some busy work to get used to working with it, but also to see kind of what happens. And so I'm going to make S3 under composition is going to consist of the identity 1, 2, 3, 1, 3, 2, 1, 2, 1, 3, and 2, 3. Kind of running out of room over there. 1, 1, 2, 3, 1, 3, 2, 1, 2, 1, 3, 2, 3. And so to try to fill this out, we would just go through. I know the identity here. And all right, maybe you guys can help me out. What's 1, 2, 3 composed with 1, 2, 3? Is that 1, 3, 2? And then the identity. And 1, 2, 3 composed with 1, 2 is 1 goes to 3, 3 goes to 1, 2 goes to 2, and then 1, 2, 3 composed with 1, 3 is going to be 1 goes to 3 goes to 1. So this is 2, 3. This is 1, 2. If I continue, this is 1, 1, 2, 3. 1 goes to 2, 2 goes to 1. So this is 2, 3. 1, 2. And then 1, 3, 2 with 2, 3 is goes to 3, 3 goes to 2. So it's 1, 3. All right. If I continue with this 1, 2 composed with 1, 2, 3. 1 goes to 1. This is 2, 3. This is 1, 3. This is 1. 1 goes to 3 goes to 2. 1, 2, 3. Sorry this is taking so long, but that's kind of the way some of these problems are, is we just have to write them all out. So here I get 1 goes to 2. Here I get 2 goes to 3. Here I get 1 goes to 2, goes to 3, and then 1, 1, 3, 2. And I think I'm finally on the last row at least. So this composed with this is 1 goes to 2 goes to 3. And then 2 goes to 2. Yep, that's right. And then 2, 3 composed with this is 1 goes to 3 goes to 2. And then 2, 3 composed with 1, 2 is 1 goes to 3, goes to 2. And 1, 2, 3, and 1. There we go. All right, big list. Now we have to make even more lists. There's my Cayley table, so I can refer to that as needed. I have to do, it is, because you kind of have things filled in, and you know that you have to have one of each of them in each row and column, and kind of like a Sudoku puzzle. So as you start filling it in, things get easier and easier. It still takes time. There were 36 things we needed to do there, so there you go. Anyway, I want to find the right cosets of the group generated by 1, 2, 3. So the first thing I want to do is find the group generated by 1, 2, 3, which is nice that we have this. Because if I want to find the group generated by 1, 2, 3, it's going to be the set consisting of, I have to close this under products, right? So what's 1, 2, 3 composed with 1, 2, 3? 1, 3, 2. And then 1, 2, 3 composed with 1, 3, 2 is 1. And then if I compose these two, I end up in there, these two I end up in there, these two I end up in there. So if I compose any pair of those, I end up back in that set. I have the identity in there, I have inverses, therefore that is a group. So this is the group generated by 1, 2, 3. Makes sense so far? So I know that this is where I start. So I just want to say, remember that I'm running out of room, but products, identity, and inverses. So I'm going to start by closing under products. So 1, 2, 3 composed with itself. Well, actually compositions in this case instead of products. But 1, 2, 3 composed with itself is 1, 3, 2. Composed with itself is the identity. Composed with itself is 1, 2, 3. Now I would actually take 1, 3, 2 and 1, 2, 3, but again I get the identity, and here I get back in here. So now I'm closed under products. So I just kept going until I was closed under products by composing it with itself and then checking that every pair of these composed together is back in this set. So I've moved on from this one to this one. Now check identity. Is the identity in there? Yes, it is. There it is. So I move on to inverses. Does each element have an inverse? Well, the inverse of this is this, so that's in there. Inverse of this is this, and the inverse of this is itself. So this is now, so all I did was each step of the way kept closing it under these things, and now that I'm closed under all three, that is the smallest that I could have that would be a group containing this. And I can stop because it's closed under all three. Does that make sense? All right. All right, so now I need to find all of the right cosets, which means I have to find all the things of the form HA such that A is an element of S3 and H is this group right here. All right, what does that mean? It means I have to take every one of these elements and multiply every one of these elements on the right. So for example, if I found H, the identity, what would that be? Is what's 1, 2, 3 times the identity? Well, that's 1, 2, 3. So this one should be on the right. So 1, 2, 3 times the identity. 1, 3, 2 times the identity is 1, 3, 2. Identity times the identity. So I get 1, 3, 2, comma, the identity. Does that make sense? Then I'm going to do the same thing for all of these. So let's do 1, 2, 3 on the right. So I'm going to pick the elements in here. These are going to be on the left. 1, 2, 3 is on the right. So if I take 1 times 1, 2, 3, I get this one, and this one. So I end up with that set. So H 1, 2, 3 is just
exactly the same thing, isn't it? I know it's a different order, but it's the same thing. And then I do the same thing. I take these three on the left by this one. So this one's 1, 2, 3, 1, 3, 2, 1. The first one was 1, 1, 2, 3, 1, 3, 2. But since it's a set, order doesn't matter. You can rearrange however you want. So what I would say is that I have H1 is equal to H is equal to H1, 2, 3 is equal to, and actually it's going to be equal to H1, 3, 2 as well, isn't it? Because if I take this times 1, 3, 2, I get 1, 3, 2, 1, 1, 2, 3, which is the same elements. So to put that out, so this is H, just to keep that up here, and I would say H1 is equal to H1, 2, 3 is equal to H1, 3, 2 is equal to H, which is equal to this setup here. Notice that if I hadn't made a Cayley table, I'd have to do each of these products each time, which is why it was worth spending the initial time to make the Cayley table. It's because now I'm able to do these sets or cosets a lot quicker. Yes, there was an initial investment, but now we can go through fairly quickly. I still have to check more, so let's find H1, 2. So these are on my left, and now 1, 2 is on my right. So what do I get is 1 times 1, 2 is 1, 2. 1, 2, 3 times 1, 2 is 1, 3. And 1, 3, 2 times 1, 2 is 2, 3. So that would be the right coset of H by 1, 2. Make sense? And actually, I can read this off fairly quickly. If I take 1, 3, what am I going to get? Is 1, 3, 2, 3, 1, 2. So it's actually the same thing, isn't it? And H2, 3 is 2, 3, 1, 2, 1, 3, which is the same thing. So what I'm claiming here is that H1, 2 is H1, 3 is H2, 3 is 1, 2, 1, 3, 2, 3. So if I had to find all right cosets, all of the right cosets are going to be, well, there's only two of them. There's H, and there's H times 1, 2, or which is also equal to these as well, which is equal to this. So it'll be two right cosets. Does that make sense to everybody? So I would say the right cosets are, there are two of them, H, H1, 2, and then I'd actually give what each of those are. So H is equal to this, and H1, 2 is equal to this. Now, just to check our work a little bit, remember we proved that each of the cosets has to have the same cardinality. Each one of these has 3 elements in it, so at least it's given us hope that we did it correctly. But we did do it correctly, we can see from the Cayley board. It's just nice to always check. What would happen if I wanted left cosets? Yeah, because there was the group generated by 1, 2, 3. Instead of having to write the group generated by 1, 2, 3, I just called it H just to make it easier. But what we said was H was the group we're interested in is the group generated by 1, 2, 3. So that's the subgroup we're interested in. So if you wanted to, you could say the group generated by 1, 2, 3 is this. And the group generated by 1, 2, 3 with this on the right is this. Now, we didn't spend time in class going over left cosets, but if you do left cosets, you do the same thing. You just put this on the left. So if you found, say, 1H, you would take this on the left, and you'd multiply this direction by the set, and actually end up getting the same thing. Put this on the left, you get the same thing, you get the same thing. And actually, in this case, the left cosets are going to be exactly the same as the right cosets. Which, if you did the homework later on, you noticed it's not always the case. But it is not always the case. It is a very special situation, which we will talk about in a further chapter. If we get that the left cosets are equal to the right cosets, we're going to end up calling this a normal subgroup. But not all subgroups are normal. Therefore, the left are not always equal to the right. So anyway, just some foreshadowing there. But again, this was just, to find all these was actually a lot of just go through and find the calculations. Make a Cayley table and then start keeping track of sets. Is that all right with everybody? Welcome. And I mean, eventually the goal is to find some type of elegant proof for that so that you don't have to do all of that work. And so if I look back now and say, could I have done that elegantly and not had to do a brute force proof? Yes, there's probably a way. But when you're initially trying to find those things, really the best way to do it is just sit down and start writing out those products until you see what's happening. If you want some type of proof later on, that is part of what you would do then is say, hey, is there some way I can use properties of these things to get this out? And there is some way to do that, but we're not quite there yet. So we'll just say, let's find these things and figure out what they look like. All right. Let me see, which one was next? I forget where we were. Chapter 16, number 7. Did I assign number 7? I didn't put it in here. Man. Alright, that means I have to go look that up real quick. I did not assign it. Alright. Let me see. I'm going to look up on Blackboard just to make sure, T, but Kelly's saying that you were looking at the wrong problems. Alright. So for chapter 16, we had 1, 5, 10, 11, 12, 13, and 16. So we did not have 7, and we did not have 15, and we did not have 21. So none of those other ones you wrote in there were actual homework problems. I can still pull them up and see if they're similar. If I can figure out where that's at. Alright, so let's go to number 15, or chapter 15. We have number 7. What is the order of Z4 cross Z7? Oh no, that's 15. I'm on to 16, aren't I? Alright, number 7 was verify that if H is equal to X cross X such that X comma X such that X is a real number, then H is a subgroup of R cross R. Describe the right cosets geometrically. So, yeah. I could see why that caused troubles. To verify that it's a group is not that hard. We just have to let A and B be in there. So we'd have something like X, X, Y, Y. And so the inverse of Y, Y would be Y inverse, Y inverse. So you'd have to show that X times Y inverse is in there. But that's actually correct. Finding the cosets becomes a little bit more difficult, which is why I kind of left this one off. And so I'm just going to skip over that one. If you want to, you're welcome to work through that, but I'll leave that one alone. The ones we did have is really 10. Sure, I can. But I was going to do 10, 11, 12, and 13. The whole point, and even 16, was actually you're kind of doing the same things you were just doing, except for you using left cosets instead of right cosets, which I talked about briefly up on the board over here. And so what we want is to say, okay, well, what if we change the ordering, A inverse B instead of A, B inverse? Well, we get left cosets. So we get things like A times H instead of H times A. And so they go through, and the point of these problems was just to rewrite those. And so actually, I think I did that anyway. So if you want to denote a subgroup I, we define the equivalence of as A inverse B is an H, then that's an equivalence relation. And if you follow through the proof, you just switch the ordering, you get, yes, that is an equivalence relation. And you get that A inverse B is an H if A is equal to BH for some H in H. So basically you're just putting the elements on the left instead of the right, and you get left cosets instead of right cosets. And this is number 12 that I gave you, is that if G is a commutative group, then AH is equal to HA. Why would that be the case? Well, if it's commutative, you could just switch the ordering, so that's going to follow fairly quickly. I'll let you guys look at that if you want. Here's an example I showed where if you find the left and right cosets, they're not going to be the same. And maybe we'll do that one. But what we had is, I'll do this one first because James asked, is if I want to find the left and right cosets of H equals the group generated by 1, 2, 3, notice I've already done that, haven't I? Sorry. So what we said was that, and because I was trying to foreshadow a little bit, we said 1H was equal to H1, and we said 1 times H was the same set. And then the same way we did 1, 2 times H would be 1, 2 here times H. So I'm going to get these three elements. So that's 1, 2 times H, or the left coset, which is indeed the same elements as I had before, perhaps in a different order, but it's the same elements. So 1, 2H is indeed equal to H1, 2. 1H is equal to H1, and then 1, 2, 3H is the same. So we have the left cosets are this one for if I'm picking any of these elements. The left or right coset is going to be this set. And if I pick any of these elements, the right or left coset is going to be this set. So they will indeed be the same. All right. Let's go back to the previous one. I'm going to pull that up because that's an interesting example and kind of goes to some of the questions you guys had anyway. Let's stick with S3. So we already have the Cayley table up there. What we need to do is just find the left and right cosets of the group generated by 1, 2. So in this case, H is going to be the group generated by 1, 2, which is the set consisting of 1 and 1, 2. I think they actually give you it's a set consisting of 1 and 1, 2. But if I start with 1, 2, I compose it with itself, I get the identity. So I'm closed under compositions here, closed under inverses. So I do have, this is the smallest group containing 1, 2. All right. Now, let's say something like the right coset, H1, is going to be equal to what? Well, that means 1's on the right. And so I'm highlighting these two elements on the left. And so I'm going to pick these 1, 1, 2. Is this the set 1, 1, 2? It is a lot easier when you have the table because you can just read it off. And so again, I'm going to move on. The next one's going to be, this is going to be my next right coset. So that is H1, 2, 3 is going to be the set consisting of 1, 2, 3 and 2, 3. And the next one is the right coset with 1, 3, 2 is going to be 1, 3, 2, 1, 3. And then if I move on to 1, 2, I get 1, 2, 1. If I move on to 1, 3, I get 1, 3, and 1, 3, 2. And then 2, 3, and 1, 2, 3. So each of my right cosets are actually just this and this, 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 and this and this. So we can read them off fairly quickly. Does that make sense? How about the left cosets? Well, then what I would do is highlight this one and this one. And again, I'm going to read across. So I'd have 1, 1, 2, 1, 2, 3, 1, 3, 1, 3, 2, 3, 2, 3, 1, 2, 1, 1, 3, 1, 2, 3, 2, 3, 1, 2, 3. All right. So why are those not the same? Well, notice that 2, 3, H is equal to 2, 3, 1, 2, 3. Sorry, 1, 2, 3, 2. And then H, 2, 3 is going to be equal to this times 2, 3 is 2, 3, 1, 2, 3. Are those the same? Is the set 2, 3, 1, 3, 2? No, they're not. Very good. They're not the same because 1, 3, 2 is different than 1, 2, 3. So now actually if you check, a couple of them will be the same. Like if I use 1, it's the same both ways. But here is one example where the left coset is not equal to the right coset. And in general, if you find each of the sets as a collection are not going to be the same because there'll be some right cosets which are not left cosets. But here would be one example where the left is not equal to the right. And so, again, I'm just following through, reading off the Cayley table to get those sets. I looked at one example and noticed that the left was not equal to the right, so there are cases where left and right cosets aren't the same. Does that make sense? Notice on the homework I worked with S3 a couple of times on purpose because I knew it was a lot of work to write the Cayley table down, but once you had it, you didn't have to keep rewriting the Cayley table because you had it, so you could refer back to it to do each of these other ones. Were there any other questions? Okay. Well, thanks for joining me, guys. I appreciate you talking in Discord there. It's nice to have the interaction. So, with that said, though, I'll let you guys go, and I'll see you on Wednesday where we'll talk about something new.